So now we're ready to talk about functions. And before we get to the abstract idea of functions, which I will spend a little bit of time talking about, and I have some videos that kind of explain some basic terminology in regards to functions, what I want to do is I want to talk about what's called Euler's identity. Euler was a Swiss mathematician, one of the most prolific mathematicians who's ever lived. He published something like 1,500 papers. I doubt there's many mathematicians that read 1,500 papers, but his name is basically everywhere in calculus and it's all over math. So he's one of the most important mathematicians that's ever lived. Euler's identity, there's so many things named after him, but this is one that just is very clearly named after Euler. Euler, by the way, is where it's why we use the letter E to denote that number, 2.7 whatever. But Euler's identity also has to do with exponentials, and it has to do with complex exponentials. And so what Euler's identity says is that if you were to take e to the I theta, and so what this now is going to be our first function that we're going to look at kind of in a systematic way as a function of complex variables. But if you take e to the I theta, what you get is cosine of theta plus I sine of theta. Okay, and so e to the I theta is cosine of theta plus I sine of theta. Okay, that's a very big deal. That's a very useful thing for us to know. This is going to come up basically every video from here on out. Okay, so this is called Euler's identity. A consequence of this is that e to the I pi plus 1 is equal to 0. So some people like to freak out about this, and it has all the 5 fundamental constants. So e, pi, I, 1, and 0. So those are kind of the 5 most important constants that people can think about. It's just a consequence of Euler's identity. I think it's more interesting that this statement is true in general. So what I want to do is I want to justify this. And to justify this, I'm going to cheat just slightly. We don't quite have, I'm going to talk about power series, but we haven't talked about complex valued power series, though we will. So what I'm going to do is I'm going to cheat just slightly, and I'm going to remind you that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. This should be a plus, and so on, x to the 4th over 4 factorial. All right. I'm going to remind you that sine of x would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Okay, and finally cosine. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on, minus x to the 6th over 6 factorial. All right. And so what I want to do is I want to look at e to the I theta in terms of its Taylor series and what we know about the Taylor series for e to the whatever, e to the x. And so this, of course, is going to be 1. So I'm looking here at this Taylor series, but this is 1 plus I theta squared over 2 factorial, I theta cubed over 3 factorial. Let's go up to the 6th power at least. I theta to the 4th over 4 factorial, I theta to the 5th over 5 factorial, I theta to the 6th over 6 factorial. And let's stop there. And so now what we can do is we can simplify this and think about powers of I that we've already talked about. So this will be 1 plus I theta. I squared is minus 1, so this will be minus theta squared over 2 factorial, minus I theta cubed over 3 factorial. I to the 4th is just 1, so this is plus theta to the 4th over 4 factorial. I to the 5th is I to the 4th times I, so 1 times I, or I. That's I times theta to the 5th over 5 factorial. I to the 6th is minus 1. And so you can continue this pattern as much as you like. But what I want to do is I want to separate the real quantity from the imaginative, from the stuff with the I in front. So I'm going to separate the real part from the imaginary part is what I want to say. So this is going to be 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on. And then we can factor an I out of the rest of it. So what we just did takes care of the stuff without the i's in it, all the even terms. And then all the odd terms, we're going to be left with something with an I in front. So we'll factor out the I, and then we're left with theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on. Okay, and of course this is just cosine theta plus I sine of theta. Okay, and so that's a justification anyways. Again, it's not a 100% bulletproof justification, because with complex series, there's some technical issues, but it turns out this is totally fine. It's just that we don't know that it's totally fine yet until we talk about complex valued power series. One alternative, by the way, is an alternative way to do this. And this is what I think the book does. So an alternative way is just to say, we're going to define e to the I theta as cosine of theta plus I sine theta. Okay, so we're going to pretend that this e to the I theta is some new function, and then they define it exactly like this, and then they derive all the other properties from it. Now, the reason why this notation is useful is that if you were to take some generic complex number z, which is x plus iy, then e to the z gives us our polar form, because what happens is you get e to the x plus iy, which is e to the x times e to the iy. And actually, I need to justify that just slightly. But e to the x is just e to the x. Some real, x is a real number, so e to the x is just some real positive value. It's just the usual e to the x curve. E to the iy is cosine of y plus I sine of y. And so if you think of this e to the x term as our r, and if you think of our theta term as y, then e to the z is really this complex number, and this gives us polar form. Okay, so this is the polar form of that quantity. So again, the polar form, if you remember, just as a quick reminder, if you have some complex number, I shouldn't use x and iy here, but you want to talk about this complex number in polar form, you talk about its the length of the line segment connecting the origin to that point, plus the angle that it makes with what we would think of as the x-axis, the positive x-axis, okay, the positive real axis, I should say. Okay, so again, that gives us polar form. So it's another way to think about this. I do want to justify this step, actually. So I want to justify why this works the way it does. But again, this is actually a story that we've seen already in this class, just not, it's just dressed up a little bit. So what I want to do is I want to show some properties. I want to justify some properties of e to the z. Okay, and so I want to think about, let's talk about some of these properties here. And there's some intricacies to be sure. Okay, so the first thing that I want to do is I want to show, let's see. So the first thing I want to do is let's talk about e to the 0. And e to the 0, e to the I 0 is what I mean. E to the I 0 is cosine of 0 plus I sine of 0. And this gives us the usual 1. Okay, so e to the 0 is still 1. Now, one complication here, and this is kind of an artifact of polar form, and this is going to be an issue that we'll have to contend with over and over. But if I were to pick some point, and this has some angle theta, so the polar angle of this point is theta. Let's make the point green just so it's a little easier to see. Then theta can be its polar angle, or theta plus 2 pi can be its polar angle, or theta plus 4 pi, or theta minus 2 pi. And so what we have to do is we have to kind of make a decision about what are the values of theta that we're allowed to have. Okay, so we need to decide what values of theta are going to be allowed. Okay, and so typically what we'll do is we'll find a interval of length 2 pi to talk about values of theta. So sometimes it's going to be from 0 to 2 pi. Sometimes it'll be from minus pi to pi. It could actually be from 100 pi to 102 pi. I mean, it can be whatever we want, really. And typically, we're not going to include the endpoints for reasons that we'll talk about later, for reasons having to do with continuity. So this determining the values of theta that are allowed is called determining a branch cut. We'll talk about this in due time, but the point here is that if I were to take e to the 2 pi I, that would also be 1, because e to the 2 pi I would just be cosine of 2 pi plus I sine of 2 pi, which is the same as cosine of 0 plus I sine of 0. And so the imaginary part of the exponential is periodic with period 2 pi. So one of the things that's going to be an issue is when we're determining the inverse function of the exponential. In other words, when we're talking about the logarithm. In order for the logarithm to be well defined, we need only to have one possible branch cut. So we need to come up with a branch cut first, and then we can talk about this function and its inverse. And so that's a subtlety that's not present in the real valued functions. Okay, and so anyways, these are some properties so far. If I were to determine the magnitude of e to the I theta is just this number cosine theta plus I sine theta. We know that the magnitude of a complex number is going to be the square root of the sums of the squares of the imaginary part and the real part. So you take the square root of the sums, so I just said a lot, but square root of the sums of the squares of the real and imaginary part, and it turns out that what we get is 1. So e to the I theta, so e to the I theta is always a point on the unit circle. Okay, so the main thing, and I want to write this very clearly here, e to the I theta in the modulus of e to the I theta is 1. Okay, so the magnitude or modulus of e to the I theta is 1. Okay, a few other properties to talk about. If we were to take e to the z times e to the w, let's say z is x plus iy, and w is, say, a plus ib. Let's think about what this quantity would be. So e to the z would be e to the x plus iy. E to the w is e to the a plus ib. And so I want to look at what's going to happen here. And this is going to end up being e to the x times cosine of y plus I sine of y times e to the a cosine of b plus I sine of b. Okay, just applying the definition of the exponentials twice. And now these are values that we can just manipulate. So e to the x and e to the a are real numbers. And so what we can do is we can kind of multiply everything, look at the real and the imaginary parts together. And so let's do that. And so we're going to end up with, we'll need a little bit more room here, but we're going to end up with the e to the a and the e to the x we can actually just factor out. And we're going to end up with cosine of y times cosine of b minus sine of y sine of b plus I. So that's the first terms multiplied together and the last terms multiplied together, and that minus was the plus I squared, and then plus the middle terms, the inner and outer terms. So this will be plus I times sine of y cosine of b plus sine of b cosine of y. Okay. And so if we think about our trig identities, this is going to be, the stuff in parentheses is going to be cosine of y plus b plus I sine of y plus b. And the exponential terms are just real, so we already know that we can add the exponents. And so what this is, if you think about this is e to the z plus w, because what's z plus w? Well, z plus w is x plus a plus I times y plus b, right? And so that's exactly what this is. So it turns out that complex exponentiation has many of the same properties that we want, e to the z plus w. Okay, so this has many of the same properties that we expect and that we have from the real analog. Okay, so from the real version of this. Okay, and so that is basically what I wanted to say about exponential functions for now. There's a few other properties that we can define, but these are the main kind of features of the exponential function.